last week we go over some example about the tension member regarding the capacity versus demand check. So today we'll continue example 3.3 where we discussed last week. Example 3.3. So for this example, I think we briefly mentioned last week. This is a double angle, and steel is A36, and the hole are half-inch diameter bolts. Assume U is 0.75. So AE is equal to 0.75 times A net. So determine the design tensile strength per LRFT. Determine allowable strength for AST. So this double angle 5 by 3 by 5/16 and long leg back to back. So meaning this is 5 and this is 3. And thickness of the angle is 5/16. So this member under tension load. So if you see double angle, you have two approach. You can either just consider single angle calculation and double the result in the end. Or you can consider double angle section property in the beginning and carry out your calculation. So for double angle property, if you want to do approach 2, there is a double angle shape property in part 1 as well. So in part 1, you have single angle, you also have double angle. So either way, you can do it. In this example, we use approach 1, meaning single angle, and then we double the result. So for one angle, let's start from the yield strength capacity check. So calculation. So based on one single area, A36 FY36 KSI. If you go to manual part 1, check 5 by 3 by 5/16 single angle. The area is 2.41 inch square. So you end up with 86.76 kips. So this is based on the yielding nominal strength. So I leave this exercise to you, so we don't need to spend time to get this number. You guys should already be familiar with how to find a value through the exercise we did last week. So if there's a two hole in each angle, now we are going to calculate fracture strength. For fracture strength, we need to calculate net area. So for net area, we are talking about a fracture. In this case, fracture. So how many hole diameter you need to subtract from AG? You got 1?
2.
2, that's correct. So you got half diameter plus 1/8, like I told you, and then times thickness of the angle, then the total area minus this, the bore hole area, but you have two bolts, so times 2. So your net area is 2.019 inch square. So the effective net area, 0.75 times A net, you got 1.514. So the nominal strength based on fracture is 87.81 kips. Okay, so The design strength based on yielding will be phi T times Pm. So it's 0.9 for yielding times 86.76 is here based on the yielding nominal strength. So we end up with 78.08. The design strength based on fracture will be 0.75 times 87.81. You got 65.86. Any questions so far regarding all the calculation?
Can you go back to the previous slide, Professor?
Okay.
Where did the 1/2 plus 1/8 come from?
Which one?
In the calculations, it said times 1/2 plus 1/8. Where did that come from?
You talking about this one?
In the next slide.
Okay.
The 1/2 plus 1/8, the very top equation.
This one?
Yeah. Where did that come from?
It's a 1/2 inch diameter.
Okay.
Time plus 1/8. That's our requirement by the code.
Okay.
Mm-hmm. Let me go back. I think.
We're okay. Thank you.
You okay? Okay. Any other question or discussion so far?
No, sir.
Okay, great. So from this result, you can tell which one govern, which one will fail first.
Fracture.
Fracture, that's correct. So this is based on a single angle, but you need to double the result. So this one governs, so this one times 2, and this will be 132 kips. This will be the capacity per ARFT for this member. So if your load reach 132, you will fracture first before yielding. So this is the capacity of this tension member. Any questions? Any questions or discussions? No? Okay, now if you do ASD, if we use allowable stress approach, so for allowable yielding, stress is 0.6 Fy. So 0.6 times 36 is 21.6 KSI. And times Ag, this will be allowable tensile load based on yielding, is 52.06. For fracture, the allowable fracture is 0.5 Fu. Fu for A36 is 58 KSI, so it's 29 KSI. So 29 times AE, that you already did the calc in previous slides, then you got 43.91 kips. So these are allowable loads based on yielding. This is allowable load based on fracture. So in this case, still fracture cover. So the allowable strength for double angle will be 2 times this value, is 87.8. So based on ISD, if your surface load combination reach 87.8, the member will break, fail at fracture at the next sections, not yielding. So this is what it means. So based on RFD, your effective load 132, you will fail in fracture. Based on surface load SD 87.8, it will also fracture for this tension member. So this will be the result for this calculation. example for double angle. So actually it's not that difficult. If you guys wish, like I said, you can try approach 2. You take the double angle property in the beginning. So I guarantee you will get the same result in the end. Okay? But don't forget, if you do double angle in the beginning, don't forget, when you make a cut to find the A net, can you guys tell me how many bolts being cut? If you consider double angle in the beginning.
Before bolt.
4 bolts, that's right. Because each angle you cut 2. But you consider 2 angle in the beginning, double angle in the beginning. So for each and every section cut, you cut actually 4 bolts. So you end up with this calculation times 4. And this is double. So actually you got the same result in the end. Okay? But you guys can give a shot to try to see if approach 2 give you the same results for approach 1. Any questions or discussions?
I did have a question on part B.
Okay.
When you were solving for the allowable stress approach, you did the FT times the 0.6 FY.
This is by the specification. This is from specification equation.
All right. I just wanted to make a note in my notes. Okay.
Yeah, this is based on the code requirements. So it's nothing special. It's the equation. So allowable yielding is 0.6 Fy. Allowable fracture stress is 0.5 U. So this is by equation, by code. So nothing special. Okay? Any other discussion or questions? Can I move on to the next slides, or you guys have any questions?
No questions.
Okay. Okay. Example 3.4 is to do detailed calculation about the U factor, the shear leg factor. From example 3.1 up to 3.3, we cover now the factor U is given in the problem statements. But like I said, that's because those example is placed in the book before it introduced the shear leg effect. So later on in the homework and also in the exams, the U factor, you either need to do the calc yourself or you need to check the code. So it will not be given in the problem statements. So in this example, I would like to introduce you to do the detailed calculation to figure out the factor U for shear leg. So determine the effective net area, we call A sub E, right? For the tension member shown in this figure. So how do you determine effective net area, which is equal to U times A net? So I think you guys already know this. Very well. So I'm going to show you how to calculate this factor U, and you guys are already being familiar with A net calculation. All right. So let's focus on one by one for this calculation. So this is a cassette plate, and this is a tension member, which is 6 by 6 by half angle. And then the bolt's diameter is 5/8. And the spacing between the bolts
1 inch.
is 3 inch along the loading directions. Okay? And then, if you look at the section cuts, you will see this section view. So on the bottom, this is cassette plate. And the hedge area is the angle, the tension member we are focusing on now. All right? So, the centroid of this angle to the connecting plane is 1.67. This number will not be given in the exam, in the other homework assignment. You need to figure out this number. Okay? So why don't you guys go to manual and go to part 1 and go to angle 6 by 6 by half and tell me, can you figure out this number? If yes, and put on the chat or put on the feedback, let me know if you can figure out this number. So far, this problem is given to you, but like I said, it may not given to you in other example. So why don't you go to part 1 of the manual and can you look out this number?
Yeah, it says 1.67 in the 13th edition. Yeah.
Do you guys get it? So I believe if you go to the manual and there are 2 axes, right? Mm-hmm. One is, I believe, they give you this, another one somewhere is here. So they give you the distance for X bar. This they call X bar, I believe. And another one they call this is Y bar. Okay? So because this is symmetric, so the X bar and Y bar value should be the same.
Yeah, they don't show a Y bar, I think, for the angles because they're the same. They might for the other ones, but I'm not seeing a Y bar for the angles.
Y bar, they do. They do have X bar and Y bar. Double check.
I see a Y bar, but not an X bar.
Same here.
X bar, let me see. 6 by 6 bar.
Yeah, I'm only seeing an X bar, not a Y bar.
X bar.
The X bar should be on the next page.
It's on the next page. That's correct. If your PDF is on next page, mine is hard copy.
They're both there.
I see. Yeah.
There should be. There shouldn't be only one.
Links. Yeah.
Okay.
Mm-hmm.
Got it, Andy?
Yeah.
So there should be 2 values.
So the one that you give us right there, the 1.67 that's shown in your example, that's X bar?
In this case, X bar equal to Y bar because they are symmetric.
Right.
If in the case this angle is non-symmetric, for example, 6 by 4 by half, then you need to figure out which direction is X bar, which direction is Y bar, based on the manual. Any other questions? You can check out any section which is non-symmetric. For example, you can check out 7 by 4 by 3/4. Then you will see Y bar and X bar. The number are different. Okay? if the angle is non-symmetric. Any other questions?
No, sir.
Okay. Then, just give me a second. Someone would like to. Okay. So with that being said, let's calculate the A net, and which is AG. Can you guys get the number AG from the menu as well? Can you tell me, can you find 5.77?
Yes.
Yes.
Okay. So that's the 5.77, and the whole is 5/8. So plus 1/8 by the code. You got 2 whole, and times thickness of the angle, you got 5.02. So this is A net. Now, there's only one element connected to the cassette plate. So meaning only one leg. So the net area must be reduced by shear leg effect. So the X bar from the manual, like I told you, is 1.67 inch. So based on the equation, U is 1 minus X bar over L. So the L is the distance from the end of the bolt to the other end of the bolt. So this is the connection length. Total is 6. X bar is 1.67. So based on this calculation, U 0.72. So AE is equal to 3.623 inch to the power 2. So any questions?
What's your
No, sir.
channel? Can you check?
So if there was only one set of bolts, then L would be 0.
If there's only, what do you mean?
So if there's 2 bolts and they're both vertical, there's no other sets. If it's just those 2 on the right, then does that mean L is 0?
Oh, you're talking about here?
No, I'm just talking about the L where you said 3 plus 3. What 3 is that referring to?
3 plus 3 because from here to here, the connection length.
Yeah, so if it was only one vertical row of 2 bolts,
Like
does
this?
that mean, yeah, would L be 0?
Then the L is equal to 0. You're correct.
Okay, so then would that ever,
Is
would
there a
we
way,
encounter
can you
that?
ask him and see if we can make those up? By any way? See if we can make the F's up?
It's a good question, but it's weird that you only put 2.
Yeah, I feel like it'd be rare to have a connection.
It's not practical.
Yeah.
Okay.
It's a good question, but it's unpractical. Because if L is equal to 0, right? And this go to infinity, right?
Yeah.
You blow up the equation. Which means the shear leg do not apply, maybe. But it's a good question. But usually we don't only put like this. No. It's not
Okay.
safe. Yeah. But it's a good question, Gary.
Professor?
Any other questions?
Yeah, for the area of holes, the 1/2 is.
Hui, can you speak louder? I cannot hear you.
Yeah, for the area of the holes, the 1/2 you got in the first equation. The first part of
Here?
is the depth of the play, right?
This is the thickness
The thickness.
of the angle, not the plate.
Yes, sir. The angle.
The angle here, we focus on this angle, not the cassette plate now. We focus on this guy first. Okay?
Okay.
Half. Any questions?
No, sir.
That 1/2 you said was from the code book, correct?
Which one? You mean this one?
The 1/2 that Yui was talking about?
This one?
Yeah.
This is the thickness.
Okay. Thank you.
Mm-hmm.
I tasted all my tea.
So, the U, like I said, you have choice. The U, you can either calculate by these equations, or you can check the table.
What do I do? Because I already finished with those.
Then you're done.
Different scenario. Remember we covered this
The
before?
other ones you're gonna mail
The
the
U?
teachers, right? See if you can
I
make them
already
up.
did them. I already texted them.
Okay, so then that's it. You're done. You're free to go. Not that
Here.
hard.
Hey, Mom. Hey, Mom. Hi, Mom. Hi, Mom. Hi, Mom. Hi, Cosita. Hi. Oh, the bone. The bone go hurt your
For different scenario,
The bone go
you can use the U value. If you meet this requirement, you can use alternative value in here. Okay? But the fundamental equation will be the one we just covered.
Why are you breathing hard, my love? Why are you breathing so hard? Why are you breathing so hard,
Here.
Mama? Why are you breathing? Oh, you're eating your
Fundamental
food.
equations.
There's ice.
Okay?
It's ice, my love.
So, like I said, the alternative value U can be used
Ice, here.
because the angle has 3 bolts in the direction of loading, meaning you got 3 bolts in the direction of loading. Okay, so the U can be taken as 0.6. So your AE is 3.012. So either U value is acceptable, but the specification allow you to use larger one to be used. Just remember. But the value calculated based on this equation is more accurate. Either way is fine. Okay? This is the information I would like to talk about. Any questions?
Will the U value always make the effective area less than the net area?
The U value will make the net area smaller than AE. So the U always less than 1. This is always reductions.
Okay, thanks.
Mhm. Any other questions or discussions about this?
No, sir.
No, okay. Now next, we talk about the welding, and let's figure out the AE for this example. So the same cassette plate, same tension member, but now we do the welding like this. In the welding along the loading directions, 5.5. And this is the angle. So, same equation apply, but now the L is equal to 5.5. It's measured from the end of the welding to the end of the welding in the loading directions. So it's 5.5. X bar doesn't change. Same cross section, So U is 0.69. So AE is 4.02. So this is for welding. So if you want to do welding instead of bolting, you got larger effective area.
Here, Mama. It's your phone, Mama. It's your phone, baby.
Any questions?
Here's the other
What
one.
does it really mean when we have a larger effective area?
Meaning you have more area to resist the load.
Got it. Thanks, sir.
Does that mean welding provides a stronger connection?
Yes, you can say so. But what's the drawback, Alex?
Installation, I would say.
Installation or of what?
Yeah, correct. Construction.
Construction, yes. Welding is more expensive than bolting. And also more involved in the labor. Okay? So everything comes with a price. The welding is stronger, but it's more cost in the constructions. Okay? So they're always good and bad. So this example demonstrates the comparison as well. Any questions?
No, sir.
Okay. Let me. Okay, so Ty is asking, would it be last longer? So Ty, what's your question? Which one lasts longer? What's your questions?
I think he was asking if welding connections last longer than bolted ones.
Yeah, I believe so. If you maintain well, I believe so. But bolt can be easily replaced. Any other questions?
No, sir.
Okay. All right. Now let's move on to one of the difficult topic in chapter 3. We call stagger fastener. So far what we cover, the hole, they are not stagger. So I will show you what do I mean by stagger. If a tension member connections is made with bolts, then the area will be maximized if the fastener are placed in a single layer, meaning a single, you can say single vertical row. But sometimes due to space limitation, such as limits on dimension A in figure 14a, for example, here. If this is a cassette plate and this is the tension member, if the geometry limitation, spacing limitation from the cassette plate here to the end of the member is limited, but you need to squeeze many bolts as you design. So you need to use stagger fastener. So this means you need to use more than one line, vertical line, to space and to place all the bolts on the member. So if so, the reduction in cross-section area is minimized if the fastener can be arranged in stagger pattern. So sometimes stagger fastener are required by geometry of connections, such as figure 14b. So like this one. Sometimes your member itself already skewed. It's not in perpendicular fashions. So if this is already skewed, what I mean skewed, meaning it's not like this. Okay? So everything is already skewed. Then this is also stagger bolts, okay, in terms of calculation. So sometimes it's by geometry of the connections. In either case, any cross-sectional section passing through hole will pass through fewer hole than if the fastener are not staggered. So if your hole is not staggered, like we talked about so far, whenever you make a cut, in this example, you cut 2 holes. If this is staggered, for each and every cut, you only have 1 bolt being cut. So you cut fewer holes compared with 2 holes when that is not staggered. Okay? But the failure path is more complicated if you stagger the bolt. So, like I said, the reason you need to stagger the bolts is because you have a spacing limitation. Then you need to stagger the bolts in order to fit so much number of the bolts. Okay? And sometimes, like I said, because of the geometry of the connection, it's already skewed. So when you calculate this kind of net area due to fracture, you already need to consider the stagger fastener layout. So with that being said, you will see that when you have a stagger fastener, you apply the loading, you'll see that the fracture is actually happening like this. And of course, it can also fracture like this. Okay, so you need to consider different loading failure paths when your bolts are staggered. So that's the reason we need to put the stagger bolts in the practical connections. Any discussions or questions?
No, sir.
Okay.
Do you mind going back to the last slide real quick?
Okay.
Professor, so what's the benefit from staggering fasteners?
Can you repeat your question, Alex?
What's the biggest benefit of staggering fasteners?
It's not a benefit, like I said, it's because of the geometry limitation, the spacing limitation that we need to stagger. Okay?
Yeah, what is the minimum distance you can have between holes?
Okay, so that will be more detailed regulation. If you go to the chapter J of the specification, they will talk about the limitation of the spacing. So it's actually a good question because there's an age, distance, and spacing requirements when you place the bolts. So that's what I'm saying. If you got limited by this number, then you already have limited space to place the bolts to following the spacing requirements. So that's why you need to stagger the bolts in order to fit the spacing within space A.
Okay, thank you.
Mm-hmm. So the only benefit I would say is to fit the limited spacing in the connection. That's the only benefit. It's nothing to really benefit of doing this. It's create a lot of problem for designer to do the calculation and to control the behavior of the connection and the member. Okay?
Are those minimum distances determined from the sizes of the bolts?
Yes, of course. Sizes of the bolt, the types of the bolts, and the thickness of the plate, etc. So they have a lot of consideration in Chapter J, connections. But now this is not your concern in Chapter 3. We will give you the layout of the bolts, the dimension, spacing is all given. You just calculate the capacity. Okay? So it's not a concern in this chapter. Any other questions?
No, sir.
Okay. So, if the amount of stagger is small enough, the influence of offset hole may be filled by a nearby cross sections. And the fracture along inclined path ABCD is possible. In such case, F is equal to P divided by A does not apply. The stress on inclined portion BC are a combination of tension and shear stresses. So let me go back to explain to you what does it mean, and then we will come back. So if your failure path is ABCD, so if the spacing between these two bolts are small enough, so when this is fractured, and it will come to this to engage the bolt, which is offset, okay, from B to C. So when you apply the loading, because the cross section now is not straight line as before. Remember when we talk about non-stagger, you cut the sections. This is 90 degrees perpendicular to the loading. But now, if you see this, this is inclined, okay? And you apply the loading like this. So On this face, you will see tension but also shear on these cross sections. So it's a very complicated situation between B to C for the stresses. AB and CD still under tension because this is perpendicular to the loading. But between B and C, the cross section is inclined to the loading, so actually have tension and shear combination. So it creates a lot of problem to do analysis and design. So several approximate method is proposed to account for the stagger Hall effect. So back in 1922, okay, almost 100 years ago, Cochrane, so this is a very smart guy, 100 years ago already proposed an idea to account for this stagger Hall effect. So what he proposed is you can deducting the area corresponding to a stagger hole, use a reduced diameter. So whenever your hole is under the line of stagger line, then you can reduce the diameter by s squared divided by 4g, become d prime. So again, d is the original hole diameter minus s squared divided by 4g. So d prime is what we call reduced diameter when the hole is staggered. Then what is S and what is G? So the S is the stagger, or we call pitch of the bolts, which is spacing in the direction of the load. So meaning is here, S, between B to C. So this is a pitch or spacing when this bolt is staggered away from B. So this is S. G is the gauge. We call transverse spacing, meaning is from B to C, the transverse distance measured from here to here, we call G. Okay, so this means in the failure pattern consisting of both stagger and unstaggered hole, use D for hole at the end of the transverse line between the hole, which is S equal to 0, and use D prime for hole at the end of an inclined line between the hole. So what does it mean? For these bolts, this is a failure path. This is at the end of the failure path, and this is non-stagger because this is perpendicular to the loading. So you use D in your calculation. But now for this hole, this is inclined. At the end of the inclined failure path, so you got to use D prime for these bolts to account for the stagger bolts effect. So this is what it means. So for this example, this bolt, you use D, no change as before. So this is non-stagger. This bolts, at the end of the failure path, this is inclined, so you use D prime for bolt C when you calculate your net area. So this is what it means for the reduced diameter approach by Cochrane back in 1922 to account for the stagger bolt effect. Any questions or discussions about these slides?
Yeah, I have one. So will the direction of failure path always start A? Will it ever start D, Professor?
You will start from, it always start from A.
So from the furthest away from the point from the load.
The first one coming, the loading is here, so we'll start from the one near to the hole. So always starting from here.
Got it. Thank you.
Mm-hmm. If your loading is coming from here, then it was starting from here. You got it, Hui?
Well, we'll start at the bottom instead
If
of
the loading coming from yes, starting from here, or you can say from here. Either way.
Oh, so let's just say
now the loading is
sorry.
coming from here, so you can either starting from here or from here. It doesn't matter.
So if you say according to what you said, then C we will be using D for C and D prime for B.
Yes. Either way, you'll get the same result.
Got it, sir.
Good questions. Any other questions for this approach?
So reducing the hole diameter would make it technically a better connection, and that's just to account for the angle that you were talking about earlier.
Yes, the D prime is to account for the stagger hole effect,
which makes it stronger.
You can say stronger or not stronger. It's not like stronger or weaker. It's not like that. It's just to account for the effect. You got to look at the overall failure path to determine the capacity. So it's not like a weaker or stronger. It's the overall effect. So far, we just account for local effect due to stagger hole. So you need to look at the overall failure path to say it's stronger or weaker. So
okay, so it's not for a stronger. It's just
our original intent is not to make it stronger or weaker. It's not like that. It's just to account for the effect due to stagger.
Okay.
But later on, when you see more, maybe on Wednesday or next week, when you do more calculation, you explore more example, and I'll go over more theory. You understand the overall picture. But now, today, you just need to know there's an approach to account for stagger hole effects. You need to reduce the diameter by this. Okay. Locally, maybe you see the A net locally maybe stronger, bigger, because this is smaller. The whole value is smaller, right? So maybe you are thinking A net is bigger, but you got to look at the overall failure path to determine actually stronger or later, not locally, okay? So we'll discuss on Wednesday, but you guys asked some good questions. Any other questions?
Yes, sir.
Okay. And also, on Wednesday, I'm going to post the homework number 2, homework assignment this Wednesday. So we will briefly go over homework number 2 problem statement in the class. So you guys can start to practice homework number 2 when I post on Wednesday, right before the class. Okay? Homework number 2 basically will be the problems you need to practice for chapter 3. Okay? So since we already covered almost half of the chapter 3, you guys can start to work on chapter 3. And like I mentioned, when we finish chapter 3 and you guys submit your homework number 2, and we will be ready for midterm number 1. And midterm 1 will cover chapter 1, 2, and 3 in the textbook. Okay? So that will be the plan for the midterm number 1. So any questions regarding homework 2? No? So
someone just asked in the chat when it's going to be due.
The due date will be to be discussed, to be announced in class, because we still covering chapter 3. So we will set up the due date when we approaching to the end of chapter 3. I would like to give it to you earlier to let you start to work on that so you can start to prepare the homework number 2 and chapter 3. So that's the reason I would like to give you homework number 2 earlier. Instead of finish chapter 3, then I give you homework 2. Then you might not have time to work on the homework and be ready for the midterm 1. So that's why I want to give you guys early homework. Any other questions?
So will the exam be next week or in 2 weeks?
No, like I say, in syllabus to be determined. So we will make sure you guys submit your homework too. You guys are okay, then I will set up the day for midterm number 1. So no day has been set yet, okay? It's to be determined. Same thing for due date for homework 2. Any other questions?
Professor, do you have any previous exams that you can provide us with?
No, I can't. Of course not. It's confidentiality, and I cannot give it to you. You just need to practice homework and the book example, and then I think you will be fine.
Okay, thank you.
Mm-hmm. Mm-hmm. Any other questions?
No, sir.
Okay, so let me think if you have any other things to talk about for today. And for your homework number 1, I will give you guys, for those of you who submitted, who make efforts, I will give you full credit if you already submitted. So that will be your homework number 1. And so you don't need to worry about the grades. I'll give you full credit for that one. The solution, homework number 1, I believe is already on Pitchboard. Do you guys have access for that? Can you download homework 1 solution?
Yes, it's there.
Okay, so great. So I think that's all the announcements that I have. I'll stay on the line to see if you have any questions. Then if not, we will continue the class. Then we'll see you on Wednesday.
Thank you.
Okay, bye-bye.
Thank you.
Mm-hmm.